Thank you for inviting me to speak about our work here. This has been a long time coming. Uh, Working closely with Dr. Tony Clevenger and Marcel Heuser, who you've heard from today earlier. And this is an effort to kind of quantify some of the longer term analysis that has been going on in Banff National Park and formed a pretty important part of my career as a scientist working in this system with these folks as my mentors and kind of growing up and under the wing of Banff's promotion of road ecology. So feel excited to share these results with you. And yes, I'm presenting from Kelowna, British Columbia, in the traditional Ontario territory of the Selk Okanagan people. So there are some, by way of background, there's some big questions in road ecology that we could probably all agree on are in the top three or top five anyways. We often want to know what causes spatial and temporal patterns in wildlife vehicle collisions. This is a photo of a badger. You can see it in the shadow of that Jersey barrier there. And this is right in front of the UBC Okanagan campus. It happened the first year I got here within actually a few weeks of starting my position. And that weekend, there was 3 badgers killed on BC's highways, and that's out of a population in the province of about 200. So it was a pretty bad weekend to be a badger. We also want to know, what are the impacts of roads on ecosystems? So how does the impacts of roads and mortality extend beyond what's going on the road itself? And then what can we do about these problems? How do we reduce collisions while maintaining or restoring connectivity? And that brings into light this, subfield of road ecology focused on mitigation. So for ease of your entertainment here, let's call that mitigation ecology. So within mitigation ecology, there are some other important questions. And one of them is, what factors may best explain species specific variation in crossing structure use? So I always harp on my students for putting acronyms in their talk, so you'll have to forgive me. I am doing that right now, but CS means crossing structure, such as this wildlife overpass. Does the type or the design of the structure or its location matter more? So could you put any old structure, if it's in the right spot, it will be effective, or does it have to be a certain kind in a certain place for it to work well? Adaptation, how does the importance of factors like width or other design features change with time since construction? So do animals or populations adapt to the presence of a structure over time? And SLOS, so this is an idea that goes back to sort of the foundations of conservation biology with respect to protected area design. Do we want one large protected area, or can we get away with several small protected areas? And that debate extends to crossing structures. Do we invest in one, really wide, well-built overpass, or can we get the same results with fewer or with more cheaper and smaller structures? So some of those questions are what motivated the analysis in the work that we did in Banff. Now, there's a problem here that I'm sure many of you are aware of, but just to put some words to these ideas, it's hard to do mitigation ecology science in a very rigorous way. It's limited when compared to other fields of science and ecology specifically. So mitigation tends to be, very expensive, as we know. It's hard to move it. It's fixed. As we heard about earlier today, there's strong and rightfully so pressure to build these structures in a risk-averse manner. So it's hard to do experiments with different types of bridges and underpasses because the risks are so high if things were to go wrong. And for some species, species with slow life histories, the response can be to these structures can be delayed. So that requires longer term investment in monitoring. And kind of going back to some of the conversation we had earlier about the Backy and the fence study that Tony presented on. Because of these conditions, there's often low statistical replication and a lack of manipulation in these systems. So that really limits the types of inference we can get away with. I'm not sure if my cursor shows up. Here we go. So you can imagine the types of conclusions you can draw from 5 data points versus 50, and it's not uncommon to see 5 structures or 5 years of monitoring in some of these studies. So how do we get around this problem of lack of replication and a lack of manipulation, experimental manipulation in mitigation ecology? One approach is long-term monitoring and relying on natural variation, or what's called mensurative experiments or mensurative studies. And that's what we're able to achieve in Banff. So for those of you who are not so familiar with this system, there's, through the course of this study, over 40 purpose-built structures along about a 90-kilometer stretch of 4-lane highway. There is phase construction. Each one of these phases was give or take 20 kilometers at a time. The first one being completed in 1988. There's upwards of 30,000 vehicles, maybe higher on long weekends. And for the purpose of this data set, these have been monitored regularly since 1996. So each one of these stars is a different structure in the study, and you can see there's different designs: overpasses, bridges, metal culverts, box culverts, etc. The data were aggregated to monthly observations, and that's in part because we had a couple different methods that were used since 1996. In the early days, they used track pads. So the folks would go out and, if not familiar, rake some dirt and look for tracks left by terrestrial mammals, count the number of animals in the direction they're moving. And then over time, we moved to camera traps when I started participating in the study around 2004, 2005, 2006. So we aggregated the observations to a monthly level because the visiting or the return interval for checking traps or checking the sand traps and the tracks was a bit irregular. And we focused on large mammals in this study: grizzly bears, black bears, wolves, coyote, cougar, both mule deer and white-tailed deer together, elk and moose. Okay, I expect everybody to memorize this table. There'll be a quiz on this at the end of the talk. So I can't hear you laughing, but I'm sure many people are. Thank you. So this is the result of the models that predicted which combination of factors best predicted species-specific variation in crossing structure use. So the point of showing this slide is, yes, it's busy and there aren't a lot of consistencies. So I'll just summarize it briefly for you. But I want to point to the idea that we looked at things like the habitat around the structure. We looked at the design of the structure, things that we can't control: elevation, distance to the built-up environment, distance to water, solar radiation around the structure. So a combination of things that were happening at the structure itself, like its dimensions, and the context around that structure, the habitat around that structure. We see a relative preference for overpasses and open span bridges for a few species: black bears, cougars, grizzly bears, and wolves. Moose, deer, and elk showed no clear relative preference for structure types. Shrub cover tended to reduce passage rates for a few species, and proximity to secondary roads increased use for black bears and wolves. And it's likely there's some different landscape contexts that are driving some of this. So some of these features are more common in some parts of the study area than others, and that could be part of the reason why we're seeing them show up in these models. So that's the big picture, but then there's these other questions within this notion of mitigation ecology that I think is where this data set has a lot to offer. So with respect to location, so here we have an example where Parks Canada built almost pairs of structures, right? So we have a wildlife underpass here adjacent to a overpass. So for simplicity's sake, these are almost in the same location if you have a large home range like a wolf or a grizzly bear. So with designs like this, we can tease apart, is it the design or the location? Now, this particular pairing doesn't happen very often, but we can look at the effect of the distribution of a or the location of the structure along the highway as like a transect, and the role that different design types had along that transect. So I'm going to walk you through quickly what the model outputs from this work will look like in a hypothetical context, and then show you what the data um, uh, reveal secondly. So we'll get a little lesson on looking at bivariate generalized additive models. Okay. So imagine this parameter space where we have the location of the crossing structure on the x-axis. So imagine a bunch of lines here would represent where that crossing structure is in space. And then focusing on width as a key dimension of structures. That's in part because that's one of the things that really drives up the cost and is at the center of a lot of debates over how big or how expensive are these structures going to be, from overpasses that are a couple meters wide and near me and here in Kelowna to the 60-meter wide structures in Banff. There's quite a lot of variation, so that's where some of the costs can come in. So in this hypothetical example, you could see that there's not a lot of variation coming from or explained by the width, but there is a lot of variation in the location. So in other words, this model would show that being around here, see that brighter color, being around here along the Trans-Canada Highway drives a lot of the variation or a lot of the use of crossing structures, but it doesn't really matter how wide that structure is in that location. So seeing a result like this would tell us the location matters more than the width. Versus this example where the location doesn't really matter that much. We're not seeing a spike along the vertical bars. We're seeing a change on the horizontal axis of this parameter space. That tells us that in this case, wider crossing structures are more important than narrower ones, and they're more important than where that structure is. What matters most is that there's a wide structure. So that's, again, a hypothetical example of what the data could show us. And here's their interaction. Here's where we might see both width and location matter. So it's not just location, 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 the mantra of real estate agents everywhere, but it's, the right structure in the right location. You would see variation like this. Okay, so that's what I hope everybody's comfortable with bivariate generalized additive models. And here's what the data show us. So each one of these is a species-specific response to these models. The gray areas are where there's no data. So we didn't have structures of a certain width in a certain location. So the model can't extrapolate or predict beyond where we have data points for. So I'll just highlight some general trends here. So for grizzly bears, you can see that the width tends to be far more important than the location. So it doesn't matter where these structures are along the Trans-Canada Highway. What matters is that they're wide. Okay, and I think that's what a lot of folks in Banff have assumed was driving grizzly bear use of these structures, but it's nice to see the data back that up. For a couple other species, location seems to be more important than width. So we have moose using a few different or a wide range of widths, but mostly they're out on this would be the far west end of the Trans-Canada Highway. And cougar is kind of the opposite, though we don't have, again, wide structures on the east end, but they tend to be, cougar use tends to be higher on the east end of the study site. And then there's another handful of species that, this is kind of a a scientific judgment or opinion, but it does seem like across this parameter space, both width and location tend to matter. And by and large, wider structures seem to be more important than narrower ones. Okay. Same type of model outputs, but now we're going to look at two different parameters. This is width and the age of the structure. So again, this is that question of sort of adaptation. How old is that structure? And basically what we're looking for is if animals adapt to these structures over time, can we get away with using a narrower structure, right? Will that over time, when they get used to them being there, is an old narrow structure as good as a new wide one? So for moose, age seems to be far more important than the width. They seem to really prefer older structures, and narrow is just fine for them. For most species, width is far more important than age. Yep. And then what I like about the grizzly bear result is you get both. This is kind of an interesting result. So here, if you follow where the yellow markers are, grizzly bears had higher use of wider structures that were young, right? And then it kind of stabilized. But they did start using narrower structures that were old. So it's almost like by building a wider structure, by building the overpass, you've accelerated grizzly bear use by about 10 to 15 years relative to the narrower structures. I find that result interesting. But the other ones are, it's a little bit more straightforward. Okay, two more parameters. This is the SLOS debate. Does the number of structures, is the density of structures more important than the size of them? Now, the logic here is if there's a lot of structures in the, okay, so first of all, we can't remove or add structures experimentally, right? This is the problem with mitigation ecology, is we can't, take out an overpass and see if the nearby underpass gets more use. And it's also hard to manipulate the width of some of these structures. So what we can do is we have the width, that's fixed. We can see what the role of the number of structures near a focal structure is. So we looked at the density of crossing structures within a 5-kilometer radius of the focal structure. And the idea is if there are more structures in the neighborhood, and that has a positive effect on use, and actually go to my notes for this one. Okay. Deer, elk, coyotes, and wolves had higher crossing structure rates when there were fewer crossing structures nearby. And this means that it's likely if we had more crossing structures, we would likely see more use of the focal structure. Right? So, okay, let's go look at this a little bit. The number of structures, the density of structures is on the y-axis. As we get, let's focus on, say, coyotes. Okay, they used wide structures when there was a low density of crossing structures in the neighborhood. You see that for all of these. So by adding more structures, you don't get more use of the focal structure. For the green species, these other ones, the width of the structure seems to matter more than the number of structures near the focal structure. So you see these sort of vertical yellow bars. So for black bears and grizzly bears, wider structures was way more important than narrower ones and more important than the number of structures nearby. Moose and cougars in this parameter space preferred relatively more narrow structures. Okay, we then looked at some community level metrics. So species richness, or in this case, Shannon Diversity Index, which is a common metric used in community ecology studies. You can see that there were, different structures conveyed or were host to more diverse species than a greater diversity of species than others. In particular, open span bridges seem to capture a greater breadth of diversity of species use than some of the other structures. Now, I want to point out that doesn't include the rarity of some of the use. So if you had some species that were very specialized on a certain structural design, that may not be reflected in this metric of diversity. Excuse me. So in conclusion, in these multi-species systems, building a diversity in all the ways that you can, a diversity of structural designs, different widths, different spacing between structures is the best way to capture the most sort of species-specific responses if diversity of species use is a priority. And I want to make sure that people register that, because Banff does have a lot of species that use these structures. And well, I think some would argue, maybe Trevor can clarify this. Generally speaking, in Banff, a lot of them have value. Maybe some species have more value than others. So if there's a targeted group of species, this study will tell you perhaps how to design your system in a way that maximizes or is tailored to those species-specific responses. Likewise, if your system does not have as many species as Banff, but has some, then I would pull out from the study, what your focal taxa or what the taxa that you do have in your system need. It is hard to make one general recommendation that, there's one master design from the Banff study that works for all species. What we see is species-specific responses across a lot of different parameters. And that's where the diversity of design comes in. So I wanted to thank you all for your time today. And this broader report includes a bunch of work from Marcel System in Montana on 93. That was not included in today's talk, but those details are in the final report.